Hello everyone. Today I'm talking about implementing RISC-V Scalar cryptography and bit manipulation extensions in Chisel. I'm Hongren. I'm from Tsinghua University. So some background on this. The motivation for implementing them is that I was working on a project called OpenRigel. It is an open source RISC-V cryptographic hardware token, and now it is public. So the target of it is to be one alternative to YubiKey, and it is all in Chisel. So for setting up this system, I decided to use Rocket Chip as the base system. However, Rocket Chip does not provide the Scalar crypto extension, which is needed by this project. So to meet my requirement, I added the support of it. I also added the support of bit manipulation extension because they overlap a lot. So with just small efforts, I added them. Some RISC-V background. So RISC-V is an open standard ISA. It was first developed in Berkeley around 2010, and unlike proprietary or private standards like x86 or ARM, it is open and free. Now it is widely adopted, and it has many ISA extensions, including extensions we are implementing today. So last year, in the autumn last year, RISC-V ratified these two extensions, the Scalar crypto and the bit manipulation extension. The first one is called ZK extension, and the next one is called ZB extension. So one interesting thing to note here is that there is no K or B extension. They didn't get the single letter. Extension name. So we should call them ZK and ZB extension. So some brief introduction about ZK. So for ZK, it covers these paths. So firstly, it covers some bit manipulation instructions like common bit manipulation for crypto, like rotation. This is very common, and some byte reverse. It is also very common. And for some, it also covers carryless multiplication. This is used for AES Scalar counter mode, and it is very costly, so it is a standalone extension. And some ZBKX is a crossbar permutation, XBAR permutation, and we won't go to detail today. And it also has support for cipher suits of different countries, like for US, the NIST cipher suit, and for China, the Xiaomi cipher suit. So for the NIST cipher suit, it covers AES and SHA, and for Xiaomi, it covers SM4 and SM3. ZK also covers ZKI and ZKT, which the first one is entropy source extension, and the second one is data independent execution latency. These two extensions, well, I didn't implement them because I don't get the entropy source extension, and I can guarantee that my implementation is truly data independent, so I didn't claim them. And for the ZB extension, it covers the basic bit manipulation, like rotation, like byte reverse. So it is very similar to ZBKB. And for carryless multiplication, it is very similar to ZBKC. And for ZBA and ZBS, it is some useful arithmetic or some single bit instructions. And the Chisel feature we use today. So Chisel is a modern. We use in the process of implementing these extensions, we use many features of Chisel. So firstly, Chisel is a modern language because we use many higher order function in my design. So I say the modern language part is it's a user part in my design, and Chisel is for parameterized circuit because in our project we can reuse designs between our 32 bits RISC-V and 64 bits RISC-V. Also, we say that Chisel utility are useful. because like for rotation we can just use rotate right, which is implemented in barrel shifter. Unlike some Verilog implementation where we need to use combine right shift and left shift. Now let's talk about our designs. So before talking about our designs, we need to set our design goal. So for rocket chip, we know that it focuses on area because we know that its ALU is really small, which we will explain in the next slide. And in that ALU, rocket reused many data passes as much as possible. And in comparison, like Xiangshan, it focuses on frequency, so it is a big core, and it didn't focus on merging data passes. So in our design, we merged many data. Sorry about that. So let's first talk about ALU. So in the ALU, we have input 1 and input 2. By just 4 units, we can support up to 40 instructions, because like we can see that in the adder we can just inverse the second input and we can do subtraction, and for the shifter we can just reverse the input and we can do left shift by just some right shifter. And for comparison, we can just reuse the output of the adder. Now let's talk about our design. First, the overview of our architecture. So recall that a rocket ship is in order core, and we can recall that the classical in order design, we have 5 stages like instruction fetch, instruction decode, execution, memory, and write back. So in the execution stage, it often contains ALU, arithmetic logic unit. So my work is that in the execution stage, I added BKU, and then I replaced ALU with ABLU. So for BKU, you can notice that we have bit manipulation in both BKU and ABLU. That's because some bit manipulation extensions like the carryless multiplication and crossbar permutation, they can hardly be merged into ALU, like reuse some common logics. So we just separate them into a standalone unit. So first we talk about the K in the BKU. So in the BKU we implemented can support both RISC-32 and RISC-64. This is some data paths of them, like because of the hardware cost for 32 architecture and 64 architecture, the instructions for them are very different. Like in the 64 bits we have 8 S-box, and for the 32 bits we only have 1 S-box, and other modules are different. So we will talk about reuse common modules later. And in our design, we merged several instructions in one data paths. Like for encryption and decryption, we can just reuse this data path. And for some instructions, if we we can mix column, or we can just do not mix column. So these are 2 data paths, and we merge them here. And like this, we can just do not mix column. This is the character of AES. So since we are talking about characters AES, let's first do some quick AES review. So for AES, it has 2 parts. The first part is about multi-round encryption. So for encryption, we have this input. We have 16 bytes as input, and we can view it as a 4x4 matrix. And since it is a 2-dimension matrix, we can have rows and columns. So the steps in the AES are this. We can first shift 1 row by 1, by 2, or by 3, and then we do substitution, and later we mix columns like in a matrix multiplication way. At last we should XOR with the wrong key. And to generate the wrong key, we need to do another step called key expansion. We need to generate the wrong key with 16-byte or longer key via some SBox and XOR. We won't go into detail today. And now let's talk about our RTL design. So we can note that the mixed column module is different for both 32 bits and 64 bits, but we can reuse them. Like we can reuse mixed column 8 in the mixed column 64. In RV32, mixed column 8 operates on 1 byte, but in RV64 it operates on 16 bytes. So we can just instantiate 16 mixed column 8 and do that. We have the direction as a parameter because for different directions the algorithm is different. So we can see that in the mixed column 8 we have the if-else condition, and we say that the higher order functions are helpful here because we can just use map to divide the input 16 bytes into individual bytes, and we can instantiate mixed column 8 for each of them. Then for the top module, for the CryptoNist module, we can generate different RTL based on the xlearn parameter. Another example in the BKU is the Galois field multiplication. So in AES, we observe that in AES we only need to multiply a constant y in Galois field. But since we need several multiplications, like multiply by 9, multiply by 15, we need a parameterized module. So Chisel here offered us a very good example and a very good level of meta. Like we can use uint from Chisel to describe circuit, but we can use like int from Scalar to describe constant, and we can generate highly specialized circuit. Like you can see that if-else here are just Scalar, but the reduce here are actual circuit. So this is very efficient. Now let's talk about the B part in the BKU. The B part only covers the ZBC or ZBKC, and the ZBKX part. So we can see here that with many higher order functions, like we can divide the input 2 into bools and index them, and then we can just left shift by a constant. I is the index here, so it is a compiler constant, and we can just with 3 lines we can describe the carrierless modification very precisely. And for X permutation, we can also do some. We can also use some higher order functions. In comparison, we can see some Verilog example in the PR of the rocket. It has full of indices, so it is very hard to understand, and we don't know the behavior of it. For ABLU, For ABLU, the design goal is that we should merge some common logic of bit manipulation into ALU. So in the original ALU, we have many existing logics, like negating the second input and the reverse the input. So we name some example here, like for the AND negate. For AND negate, we can just implement alongside the original AND, and we can reuse the negate, and we can reuse the AND gate. Also, for some like rotation right and rotation left, we can reuse the in reverse, and we can implement rotation left by rotation right. And for C-pop, we can just use the Chisel utility, the pop count in Chisel utility. Here is the ABLU diagram. So just like before, we have adder, we have shifter, we have comparison, and we have logic. But now we add some modules like the process input, like we extracted some common patterns in the input patterns of the instructions, and we first process them and send them to different modules, different units, and like we can see that here we have some other special inputs for some like count tailing 0 or count leading 0, and for rotation, we can see that for rotation we can reuse the original reverse, shift, then reverse. Data path here we can reuse the reverse to reverse here. We can reverse, rotate, then reverse again to get the rotate left. For pop count, we have a dedicated module here. It reuse pop count in Chisel 3 utility. And for the count leading 0, we have some other special logics. You can see the RTL in our PR. Now the evaluation. So finally we use the FPGA to evaluate our design, and we can see that we can reach up to 10x for AES for RV64, and we can reach significant speedup in other tests. And the area cost is relatively small because you can see that the div module here, the ZKN and ZKS module, the div module here is for multiplier and divider, and we can see that the ZKN and ZKS module takes almost the same area of div. And for ABLU, we can see that we doubled the size of ALU, but considering that we have implemented many instructions, this area is acceptable. For experiment characters multiplication, its area is really high, but in the spec they said that it is expected that we take much area, so this is a acceptable result. So that's all of my talk. Thank you for listening.